Chapter 2 Logic, there is proposition, or we call it as a statement. This statement can be either true or false, and it cannot be both. There is two proposition, which is primitive and compound. Primitive proposition is free from logical operator. Meanwhile, compound proposition, there is exist logical operator such as or, and, implies, biconditional, and negation.
Loss of logic is used for any primitive propositions, PQR, any tautology, T0, and any contradiction, F0. For double negation, we use when we have two negation symbols. For De Morgan's, we need to multiply the negation symbol into the bracket and the operator will change otherwise. For commutative, we need to change the place between the propositions. And for associative, we use when we have the same operator. For distributive, we use when we have different operator. And for idempotent, we use when we have the same proposition. For inverse, P or negation P equivalents to T0, P and negation P equivalents to F0. For identity, P or F0 equivalents to P, P and T0 equivalents to P. For domination, P and F0 equivalents to F0, P or T0 equivalents to T0. For definition of implication, we need to change the implies operator and put the operator negation with or. Definition of biconditional, we need to change the biconditional operator and it will have operator implies and. For absorption, we use when we have different symbol and have two same proposition. To solve this question, first we use definition of biconditional to change the biconditional operator and we have implies and operator. Next, we use definition of implication and we have negation or symbol. After that, we use De Morgan's because we need to multiply the negation symbol into the bracket and the operator and will change to operator or. After that, we use associative because we have same symbol and it becomes in bracket negation P or negation P. Then we use idempotent because negation P or negation P we get negation P. After that, we use absorption because we have different symbol and we have two same proposition, which is P or in bracket P and Q, so we get P. After that, we use distributive because we have different symbols, so in bracket negation P and P, and then we use inverse because in bracket negation P and P we get F0. Lastly, we use identity because F0 or in bracket negation Q and P we get negation Q and P. To solve this question, first we use definition of implication to change the implies symbol. Then we have negation or symbol. Next, we use De Morgan's because we need to multiply the negation symbol. And again, we use De Morgan's. Next, we use distributive because we have different symbols. So in bracket negation P or P. And then we use inverse because negation P or P we get T0. Next, we use identity because T0 and in bracket negation P or negation Q we get in bracket negation P or negation Q. After that, we use associative because we have same symbol and we can combine negation Q and Q together and it becomes negation Q or Q. Next, we use inverse because negation Q or Q we get T0. Lastly, we use domination because negation P or T0 we get T0. So, to conclude, in bracket P and in bracket P implies Q, it is logically implies Q.
Next, I'm going to explain subtopic argument, which is in chapter 2. Argument is a list of given statement called premises followed by final statement called conclusion. It can be expressed as written in the brown box above. Argument is said to be valid if each of the premises is true, then the conclusion also true. There are three methods that we can use to check the validity of the argument. So the first one is by using truth table, the second one is loss of logic, and the third one is rules of inference. Right now, I will only explain in details about argument using rules of inference. Rules of inference will be used to avoid large truth table and when the argument involves more than 3 propositions. There are 11 rules of inference and those rules are as follows. Let's see example 1. Prove the validity of the argument below using rules of inference. Ami skips many classes and excels in her studies. If Ami skips many classes, then she does not excel in her studies or she is not smart. If Ami reads a lot of books, then she is smart. Therefore, Ami does not read a lot of books. First step that we need to do before we prove the validity of the argument is to declare the primitive propositions using symbol P, Q, R, and S. Then we will get like this. Next step is to write the premises using logical operators, just like this. Only then we can prove the validity of the argument. So firstly, we put the premises from number 1 until number 3. Number 4, we got P from number 1 by using rule of conjunctive syllogism. Then number 5, we got negation Q or negation R from number 2 and 4 by using modus ponens. Number 6, we got Q from number 1 using rule of conjunctive syllogism. Then we got negation R from number 5 and 6 using rule of disjunctive syllogism. Lastly, we arrive to our conclusion, which is negation S from number 3 and 7 by using modus tollens. So the argument is valid. Move on to the second example. Given the argument below, prove that it is valid using the rule of contradiction. Now let's reprove it. Firstly, we put the premises from number 1 until number 3. Number 4, we use from number 2 by using equivalence identity. Then we will get Q or negation P from number 3 and 4 by using rules of resolution. Then we will do commutative law. Number 7, we will get R from number 1 and 6 by using modus ponens. Our argument can just stop until number 7 because R is our conclusion. But since the question asks to use rule of contradiction, then we need to declare an additional premise that is contradicts with our conclusion, which is negation R. Then we will get R and negation R from number 7 and number 8 by using rule of conjunction. Then we will get a contradiction from using inverse law. Since we got a contradiction, we can say that our assumption, negation R, is false, hence our conclusion, R is true. So the argument is valid.
In Chapter 3, Proof, a mathematical proof is a convincing argument expressed in the language of mathematics, and there is 7 methods to prove, which is the forward-backward method, the construction method, the choose method, mathematical induction, specialization method, the contradiction method, and contrapositive method.
Now I will explain about the first method of proof in chapter 3, which is the forward-backward method. The forward-backward method is the method to prove the conditional statement if A then B is true, where A is the hypothesis and B is the conclusion. Not just that, the forward-backward method is also the combination of 2 ways, which are the forward process and the backward process. To be more specific, the backward process is when we identify the conclusion and we let it as B and analyze the sentence so we can simplify it into a mathematical statement by using the definitions and mathematical terminology. Same goes for the forward process. We will identify the hypothesis and we let it as A, then simplify the statement into a mathematical statement. Every step for each process that we have simplified respectively, we will symbolize the steps such as B1 for the first step, then B2 for the second step for the backward process, and same goes for the forward process such as A1 for the first step and A2 for the second step. After we show the combination of the 2 processes, the simplified step from 2 different ways will eventually meet in the middle, which means those 2 steps from 2 different processes will give the same result. Therefore, it will show that the conditional statement is proven to be logically equivalent. Now let's look to the examples. To solve example 1, firstly we need to identify the hypothesis and let it as A, then the conclusion and let it as B. A is n is an even integer and B is n squared is an even integer. After that, we will simplify B with the definition 5 of the definitions and mathematical terminology. Thus, we will get B1 is n squared equals to 2k, where k is an element to integer number. Next step, we will also simplify A with the same definition, and it will be A1 is n equals to 2s, where s is an element to integer number. At A2, we will square both the left hand side and right hand side, and we will get n squared equals to 4s squared. Next, we will factor 2 at A3, then assume r equals to 2s squared, where r is an element to integer number. Thus, we will get A4 is n squared equals to 2r. We can see that A4 has the same result with B1. Therefore, A4 is logically equivalent to B1. To To solve example 2, firstly we need to identify the information from the question, then we will sketch so that we can see the image through the question. As a result, we will get the sketch like this from the given informations. Next, we need to identify the hypothesis and let it as A, then the conclusion and let it as B. After that, from B, which is the triangle ABC is isosceles, we know that A and B have the same length. Thus, B1 is A equals to B. Then we take B to the left hand side and it will be B2 is A minus B equals to 0. Afterward, from A, we can use the area of a triangle. Thus, A1 we will get AB over 2. At A2, we will compare the area given from the question with the area that we get from A1. So it will be AB over 2 equals to C squared over 4. At A3, we will apply the Pythagorean theorem. So at A4, we will substitute A squared plus B squared at C squared. We will continue with A5 to A6 by cross multiplication. Then we can factorize the equation at A7. As a result, we will get the factorized form equation at A8. At A9, both factors are the same, so we will just square it. Then at A10, we will get A minus B equals to 0. Same result with B2. Therefore, A10 is logically equivalent with B2.
Next is the mathematical induction used when B has the form for every integer something happened when something happened depends on an integer. To prove using mathematical induction, we need to show 3 steps. The first step is P1 is true, next step we need to assume that Pn is true, and the last step we need to show that Pn plus 1 is true. Example 1. Prove by mathematical induction that for every integer n is greater or equal to 1. 2 square plus 5 square plus n square plus 3n plus 1 square is equal to 1 over 2n times 6n square plus 3n minus 1. In the first step, we must to prove that P1 is true, and we substitute 1 into k and n, so the left hand side and right hand side are equal to 4. And P1 is true. If P1 is true, we can move to the next step, which is we assume that Pn is true. Pn equal to n, k equal to 1. 3k minus 1 square is equal to 1 over 2n times 6n square plus 3n minus 1. So we take the right hand side of Pn, which is 1 over 2n times 6n square plus 3n minus 1. We substitute the n with n plus 1, so it will be 1 over 2 times n plus 1 times 6 n plus 1 square plus 3 n plus 1 minus 1. So we will simplify all the equation and we expand the n plus 1 square and times with 6. So it will be 6n square plus 12n plus 6 plus 3n plus 2. And after that, we times with n plus 1, so we will get 6n cubed plus 15n square plus 8n plus 6n square plus 15n plus 8 divided by 2. And we simplify it, so the answer is 6n cubed plus 21n square plus 23n plus 8 over 2. So next is the right hand side. We use the formula Pn plus n plus 1, which is Pn is 1 over 2n times 6n square plus 3n minus 1, and no need to substitute the n with n plus 1. Pn plus n plus 1, which is n plus 1, is come from 3k minus 1 square. The k we substitute with n plus 1. A third equation, we can expand 3n plus 2 square and times with 2 because the denominator must equal to 2. So the answer is same as the left hand side when we simplify it. So the answer is 6n cubed plus 21n square plus 23n plus 8 over 2. Example 2. Prove by mathematical induction for every integer n is greater or equal to 1. N k equal to 1, k square over k plus 1 is equal to n factorial over n plus 1. And the first step we show that P1 is true, so the answer is 1 over 2 is equal to 1 over 2 when we substitute 1 into k and n. Step 2, assume that Pn is true. Pn is equal n, k equal to 1, k square over k plus 1 equal to n factorial over n plus 1. Step 3, show that Pn plus 1 is true. So the left hand side, we take the right hand side of Pn, which is n factorial over n plus 1. We substitute the n with n plus 1, so the answer is n plus 1 factorial over n plus 2. Right hand side, we will use Pn times n plus 1. Before this, we use a summation symbol, so we plus Pn and n plus 1. But now we use a product symbol, so we must do times Pn and n plus 1. Pn is equal to n factorial over n plus 1. No need to substitute the n with n plus 1. And times with n plus 1, which is n plus 1 is come from k square over k plus 1. We substitute the k with n plus 1. At the third equation, we simplify the n plus 1 and we will get n factorial times n plus 1 over n plus 2. because n factorial times n plus 1 is actually equal to n plus 1 factorial. So left hand side and right hand side are equal. So p n plus 1 is proven.
For the conclusion, in this video, we learn how to solve questions in laws of logic and argument for chapter 2. Meanwhile, for chapter 3, we learn how to prove using the forward-backward method and how to prove using mathematical induction method.